general relativity, step by step. And when I say step by step, I mean it. What have we been doing? We've been looking at the Euler-Lagrange equations here, and I pointed out that this equation here is actually 4 equations all rolled into one. And we looked at the time component, the first component, or the 0th component, I guess, of this equation here. And we've got this beautiful result here, t dot 1 minus 1 over r equals k. Beautiful. Right, now let's do the next one. What was my Lagrangian? It was this term here, and now I need d by d tau of di L by di, we've done t, r dot minus di L di r equals 0. Well, that's going to be a bit harder because there's lots of terms floating around. Okay, well, let's just do it anyway. Let me write out my Lagrangian, and then we'll solve the equation. Okay, what was my Lagrangian? Lagrangian was equal to minus t dot squared 1 minus 1 over r plus r dot squared 1 minus 1 over r plus r squared d theta squared plus r squared sine squared theta d phi squared. And the equation that we had was up here somewhere. There it is, d by dtou, roll that up. Just a minute. D by d tau of di L di r dot minus di L di r equals 0. Okay, well let's just do it. Pinch in a little bit. D by d tau of di L di r dot. The only r dot term is this one here, so it's 2r dot 1 minus 1 over r minus di L di r. This term here is di L di r, and this is a little bit harder. We've got lots of terms here. We've got a minus, that's a plus, so it's t dot squared. Minus times a minus is a plus, but it's r to the minus 1 which we're dividing, which makes it a minus r to the minus 2, I think. Is that right? Yeah, I think that's right. Plus di L di r. R dot squared times, that's minus r to the minus 1, so it's minus, goes to a plus r to the minus 2 again, plus 2r, oh no, that wasn't a d theta, that was a theta dot, and that was of course a phi dot squared. Theta dot squared from that term there, plus 2r sine squared theta phi dot squared. And that lot equals a constant. Well, that is quite a ball-bustingly difficult equation. Look at it, it's quite hard, that. There's quite a lot going on there. I guess we could simplify it a little bit if we really, really wanted. Let's have a look at the other terms. Well, they turn out to be very similar. Theta dot dot plus 2 over r dot theta dot, just copying from my notes here, equals sine theta cos theta phi dot. Is that phi dot squared? Yeah, that's phi dot squared. Yeah, it's just the same thing. We're just going to take this Lagrangian here, and we're just going to deal with the theta terms and the phi terms. And what's the final one? What's the final one? The final one is r squared sine squared theta phi dot equals another constant, which is usually called h. So we've got some equations here. We've got, what have we got here? We've got this equation here. Oh yes, we've got this one here, which is a beautiful one. We've got this equation here, which sucks rocks. Sucks. We've got this equation here and this equation here. So what we're going to do is we're going to boot that one. We're going to bin this one. I'm just going to forget that because it's just too hard. And I'm going to remind you what the x dot beta, the variational calculus argument gave us, that g alpha beta x alpha dot x beta dot equals 1, which was, I think, the previous screencast. I'm not sure. Yes, here it was. It was that result there that I'm going to be using. So what we're going to do is to get rid of the sucky one. We've got one equation, two equations. Oh no, this equation, this equation, this equation, and also this beautiful one here, t dot 1 minus 1 over r equals a constant. Also t dot 1 minus 1 over r equals a constant. So we've got 4 equations for our 4 variables for geodesic motion of massive particles near a black hole. Beautiful. I'm going to stop there. Stop. Actually, before I do, there's just one thing I want to say. It's not immediately obvious where the Schwarzschild metric comes from. How are we incorporating the Schwarzschild metric? The answer is here in the Lagrangian. Because fundamentally, oh, well, it's here, I guess, because we're using the metric tensor in the Schwarzschild metric to calculate the Lagrangian. And we get these quite amenable equations here to solve. And I'll solve those in the next screencast. Stop there. Stop.